Hello, my name is Till Schluter and I'm going to present our paper Differential Analysis and Fingerprinting of ZombieLoads on block ciphers. I did the main part of this work together with Professor Kerstin Lemke-Rust when I was a student at Bonn-Rhein-Sieg University of Applied Sciences, and now I'm a PhD student at CISPA in Saarbrücken. I would like to start with a short recap of the ZombieLoad attack, which was initially introduced by Michael Schwarz et al. In 2019. I'm sure you all know this kind of memory hierarchy, which is quite common in modern PCs. If you load a value from memory, it goes through all the different cache stages you can see on the slide, and on Intel CPUs, there is an additional stage between level 1 and level 2 cache, which is a line fill buffer. The ZombieLoad attack targets this line fill buffer. Let's assume we have two processes, a victim process and an attacker process, and both are executed on the same physical but on different logical CPU cores. The victim process now loads a secret value from memory. The load goes through all the cache stages and also through the line fill buffer. Concurrently, the attacker executes a faulting load instruction, and the CPU answers this faulting load instruction transiently with a value that comes from the line fill buffer. The line fill buffer is shared among all the processes that run on the same physical core. So the attacker can be sure that the value that is read from the line fill buffer comes from some other process that recently issued a load request in close temporal proximity to the actual attack. The attacker now has access to the full line fill buffer entry, which is 64 bytes long, but has to decide for one of the bytes to extract using the cache. The ZombieLoad attack is a data sampling attack. That means that the attacker only knows the data value and the point in time when the attack took place, but it's unknown where the actual data comes from. So the actual memory address that was accessed is not known to the attacker. Okay, how can a ZombieLoad now be triggered? There are two variants that I would like to present to you, and you can find more variants of this in the original ZombieLoad publication. The first variant is close to meltdown. You need a memory line which is accessible through a user space address and a kernel space address. And now you use a user space address to flush this memory line from the cache, and use a kernel address to access the memory line again. And this access, as it takes place from user space, will fault and therefore gives you transiently access to a line fill buffer entry. Another variant is using Intel TSX. This is the variant 2. For this, you only need a memory line with a user space address and access this user space address after flushing it within Intel TSX region. This leads to an abort in the TSX region, and again you can access transiently the line fill buffer. Next, I would like to describe the Domino attack, which was also published in the original ZombieLoad publication, and it targets a static key that is used repeatedly in AES encryptions. The AES implementation frequently loads this key from memory to work with it. The attacker uses ZombieLoads to collect samples, byte by byte and from different positions, and hopes to leak parts of the key. But the key will not be the only value that appears in line fill buffer entries, and the attacker has the challenge of combining the correct bytes from the samples to form the key. Domino bytes makes this task easier because they are composed transiently from parts of two neighboring bytes. One half comes from the first byte and another half comes from the second byte. The Domino byte is then leaked through the cache, like the individual bytes were leaked before. The attacker can now use the Domino bytes to find chains of bytes in the recorded samples. Only bytes on neighboring positions for which a matching Domino byte exists can form such a chain and thereby are a potential key candidate. Here's an example. In the upper row you can see 16 bytes of an AES key, and in the lower row you can see the corresponding Domino bytes. So have a look at the first two bytes. They are hex 2b and hex 7e, and correspondingly the Domino byte below is hex b7. As we've just seen, the Domino attack requires access to the key, which is loaded from memory. Now let's suppose people invent countermeasures that make sure that the key is may be transferred as rarely as possible through from RAM to the to registers in the CPU, or that the key is somehow obfuscated, masked, or whatever. So we don't have direct access to the key, but let's say we still can see the algorithm working. So now I would like to present our first attack, the so-called differential attack, which targets intermediate values that occur during the execution of a cryptographic algorithm. The scenario is as follows. Let's say we have again a victim process that computes maybe an AES, maybe another block cipher, and it takes some plain text and it gives us a ciphertext, and the encryption happens with an embedded key. And of course we are interested in this embedded key, and we don't care about the ciphertext for now. Let's say the plaintext is either specified by the attacker or it is at least known to the attacker. Yeah, so let's for now say it's specified by the attacker. And as well, we have the following information. Of course, we see intermediate values of the cryptographic algorithm via ZombieLoad. Yeah? So we perform in the attacker process concurrently ZombieLoads and hope to see intermediate values. And of course, the end result should be the cryptographic key in the attacker process. So how does this attack work? First, we start with collecting samples. This is fairly straightforward. We just use ZombieLoad to collect samples from the line fill buffer from varying positions. But additionally, we take note of which plaintext was currently encrypted by the AES program when we took the sample. The next step is the analysis step. So we take the first byte of our first plaintext and we calculate the first steps of the AES. The very first step is to add the key, and as we don't know the key, we just for now take the byte value 00, hex 00, and we will use other values later on. We get a first intermediate result, which is highlighted in red here on the slide, and we can also compute the next step, which is the sub-bytes operation, and we get another intermediate result. And now we do these two steps for all possible byte values for the key. Yeah, okay, so we do this essentially 256 times. The next step is to go back to our samples, and we now try to find matching values. So we take a look at all the 256 sets of two values that we pre-computed and try to find them in our data set, in our samples. And if we find a match for one specific key hypothesis, then this is an indicator that this key hypothesis at this position is correct. And we take a note of this by writing this information into a matrix, and we set up a matrix for this with 256 columns and 16 rows. So we have one column per key byte hypothesis, per possible value of this key byte, and one row for each byte position. And in this matrix, we store counters, and each counter says how many matches we observed for a combination of this byte position in the row and a specific key byte hypothesis value in the column. In reality, this matrix could look like this. I put the first few columns of such a matrix on the slides, and now we can go for each row and find the maximum value in this row. And the column index of this maximum value then indicates the most probable key byte hypothesis. Of course, we also implemented this attack, and we used the implementation, the AES implementation AES-min, which is byte-oriented, implemented in C and very close to the standard. First, we did a preliminary experiment, and we checked which intermediate values we can observe when we sample during the execution of AES-min. And we observed that we can find all intermediate results from all operations in all rounds of the AES. And as a side note, in our case, the sampling rate is way lower than the frequency of the AES computations. That means that we should expect not more than one sample per AES computation, because our sampling rate is so low relatively to the frequency of AES computations. Now let's have a look at one position. Yeah, we sampled byte values for one position in the key, and now we are interested in in the values that occur. Mainly we are interested in the number of values that occur, because if here occurred many different values, then we would have a great impact by noise. But in this case, we could attribute most of the values that we observed actually to AES intermediate values that we would expect. So we can say that the number of values which are just noise to us, because they are not related to the AES, or at least not to these intermediate values, is relatively low, and that is fairly good for our attack. As I said, we executed the attack and we did this on different CPUs. And you can see in the first 3 rows, the first 3 CPUs, that we were fairly successful. We list, for these CPUs, we list first the fastest attack, and we list the, let's say, most reliable attack. So we can say that the fastest attack just took 3.4 seconds. And with parameters that allow a more reliable attack, it took a bit longer. It took on average 10 seconds, at least on the first CPU. Yeah, you can see in the second section here, there are 2 CPUs from the Kaby Lake generation, and we observed here that these CPUs had a different leakage pattern, and we had more noise values, so it was difficult to execute the attack on this with variant 1, but we implemented the attack again with ZombieLoad variant 2 and were more successful. So we also listed the results here in the lower part of the table. Of course, we will publish we already published the code, the source code on GitHub. You can find the link in the paper if you're interested. As a last point for this section, I also brought a small video where you can see the attacker process in action. So I will start this now. This is the attack in real time, so I didn't speed this up. We will go up to 60,000 samples, and then we will see for each position of the key the most probable key byte in the first column, which is highlighted in red here, and then there are other hypotheses which are less probable according to the analysis. Yeah, and actually we can see the correct key completely in this first line, so this attack was fully successful and was able to extract all 16 key bytes from the intermediate values of AES min in 7.6 seconds in this case. Next, I would like to introduce to you the Cache-Line-Fingerprinting attack, which is our second attack. Let's start again from a line fill buffer entry, which contains a cache line, a value of a cache line. And as we said before, we can always go ahead and just extract 1 byte from this line fill buffer entry over the cache-based side channel. As we observed in our experiments, it is also possible to access the probe array for a second time during transient execution, at least with ZombieLoad variant 1. So let's do this, but let's not use this additional capacity of the side channel to extract another data byte, but instead let's extract a byte that identifies the value in the cache line. We calculate the XOR sum of the first 8 bytes, and the result is then encoded into the cache by accessing the probe array in a second half. Yeah, so we extend the probe array to the double length, and in the second half we encode an additional byte, which is our fingerprint byte. When we retrieve the data back from the cache, we store all data bytes with the same fingerprint byte in the same place. So we set up so-called sampling pools, 1 pool for each fingerprint, and let's say for our fingerprint A4, we store the data byte that we sampled with this fingerprint in the sampling pool for fingerprint A4. So we end up with 256 different sampling pools where we can store data, and which make it easier for us in the end to find constant byte chains, like for example keys. So the main benefit is that if we observe a cache line multiple times, it will always have the same fingerprint, and we therefore collect all the samples from this cache line into the same sampling pool. Next, we want to use cache-line fingerprinting to attack an OpenSSL AES implementation, and specifically the key schedule of this implementation. We use cache-line fingerprinting to find sequences of 16 consecutive bytes and store these sequences. And our hypothesis is that among these sequences are round keys that are computed by the AES key schedule. And now we want to use this information to find round keys and to calculate back the main AES key, and all this without knowing a plaintext ciphertext pair. So how can we do that? On the left-hand side, we can already see 3 sequences of 16 bytes, which were found using Cache-Line-Fingerprinting. And we just take the first line and assume it is a round key. And now we apply the inverse AES key schedule and compute the previous round keys. And for each previous round key, after we computed it, we check if this previous round key is also among the sequences that we found earlier with the help of Cache-Line-Fingerprinting. And in this case it is. And now that we found the second round key, it is easy for us to go ahead and compute a few more steps back in the AES key schedule until we reach the last key, the initial key, the AES key. Again, we executed our attack on different CPUs, and we used ZombieLoad variant 1 in this case for all of our attacks, because with variant 2 we were unable to encode the fingerprint byte into the cache. This is due to the smaller transient execution window, which does not allow to compute and encode this byte into the cache. So as you can see here in the table, we were successful for the first 2 CPUs. We could apply our attack in, on average 11 to 12 seconds, and we were fairly successful with our attacks, depending on the leakage patterns on the specific CPUs. On the lower 2 CPUs, these are again these Kaby Lake CPUs where we had problems before with variant 1 for the differential attack. It's just that we couldn't use variant 2 as a replacement in this case. Okay, so now let's compare our attack to the Domino attack, and we see 2 advantages of our attack over the Domino attack. First, we add this additional dimension to the samples, which as a result leads to 256 frequency distributions of different values. And by this, we also reduce the noise in each of these sampling pools, because the noise is also distributed over different sampling pools, or is even contained to some sampling pools. And again, another advantage is that we sample the fingerprint and the data value always from the same cache line. This is not guaranteed with the Domino attack, because the individual bytes and the Domino bytes are sampled in different instances in different ZombieLoad iterations. And we always use the same ZombieLoad iteration, the same transient execution window to extract our values in this case. Okay, again, I brought you a small video, so let's have a look at this attack as well. We start by starting a victim process, and now we start the attacker process. Again, I didn't speed this up, and as we saw in the table before, it might take around, I don't know, 10 seconds or so, 10 to 11 seconds, and then we will see, we can see here with the prefix possible candidate, we see all the sequences of 16 bytes that were detected using Cache-Line-Fingerprinting. And for one sequence, it was detected that this is a round key, and additionally that there is another sequence that is also a round key that appears if you assume that the sequence is a round key and you use this inverse key schedule as I sketched it before. So yes, this worked. So let's go on. Next, I would like to discuss some countermeasures. Of course, first we can use the general ZombieLoad countermeasures. For example, blocking the necessary building blocks for ZombieLoad, like blocking simultaneous multithreading or hyperthreading, as it's called by Intel, or Intel TSX. Another point is co-scheduling. That means that the operating system takes care of only scheduling processes on the same CPU that trust each other. Or we could clear the critical buffers, like the line fill buffer and other buffers, on context switches. There are also some countermeasures that we could use specifically to mitigate our attacks, and especially I would like to talk about masking now. For the differential attack, we could use a masked implementation of the block cipher with random, secret, and frequently changing masks. This would lead to the fact that we couldn't use our analysis algorithm anymore because we were unable to pre-compute these intermediate values that we need. These kind of implementations are already known because they are also common to mitigate power analysis attacks. For cache-line fingerprinting, we can also use masking because for cache-line fingerprinting, we need a constant sequence of bytes from which we can generate our fingerprint. And if this is not there anymore because we use frequently changing masks, then we couldn't assign the same fingerprint to multiple observations of the same data. So let's come to a conclusion. First, I showed you our differential attack, where we used sampled intermediate results which can be used for key recovery. And our core message here is protecting the key is not enough. Yeah? Keep in mind that there may be intermediate results, intermediate values that could also leak, and could a potential attacker give more information about the data you are processing, including the secret key. This is especially important for algorithms which are not hardware supported but entirely executed in software. And additionally, I showed you the cache-line fingerprinting approach, which is an efficient mechanism for extraction of constant byte sequences from memory lines, which we observe using ZombieLoad. Yeah, finally, I would like to thank you for watching and invite you to join us in CARDIS session number 4 on Thursday.